T is 2 pi over n omega naught. The largest one is the one with n being the smallest. Because you can make n is equal to 0, then the period is infinite. There's a DC problem. Okay? N is equal to 1, then the largest period is 2 pi over omega naught. Okay? Omega naught is usually defined to be 2 pi f with 2 pi 1 over t, and this will give you back the same thing. Okay? Give you back the same thing. That is what omega naught and things are. All of this harmonics on the right hand side have the same oscillatory theory. Okay. What happens if we give you something? Like if I give you something like a signal is equal to 2 cosine of 2 pi t plus 4 cosine of 2t. Is this a periodic function? Does it fit into sums of two periodic functions that share the same fundamental frequency? There is a fundamental frequency that you can call this the fundamental frequency. And every term of this share that fundamental frequencies. It's just having higher frequencies that are multiples of the fundamental frequency. But if I give you a function like that, now you see two frequencies. Okay, one is omega 1 equal to 2 pi, the other one is omega 2 equal to 2. Can they be regarded as multiples of each other? No. So these two functions together give you oscillatory functions, but they're not periodic because the two periods are not the same. Okay, you always will get a non-periodic function as a sum. Okay, so this is not a periodic function. There's something that you have to be aware of. In order for harmonics or sinusoidal functions to sum up to be periodic functions, then they have to share a fundamental frequency. Like if I give you this one plus sine of 6t plus cosine of 7t. Is this a periodic function? Yes, because they share a certain fundamental frequency. Okay, you can see that omega fundamental is equal to 1. It's been shared by all these three frequencies. Okay, so this frequency, this signal will repeat itself after that frequency. Okay, and then there are other examples in the textbook. You can look up them and figure them out. And let's talk about the properties of Fourier series. Okay, are there any questions regarding this? Yes, Alex?
I don't understand why those are the same frequencies.
Oh, they are not the same frequencies, but they have the same periodicity that they repeat themselves after the fundamental period. The fundamental period is that of this frequency, right?
How is it one?
For the first set?
Does it have to be an integer multiple or what?
Yeah.
Integer multiples?
No. This thing means that omega f is 2 pi over t. Okay, t is equal to 2 pi. Okay, which means that this signal will repeat itself after a period of 2 pi, but this signal repeats itself 4 times faster than 2 pi. This signal repeats itself 6 times faster than 2 pi. This signal repeats itself 7 times faster than 2 pi. Okay? But after 2 pi, they are in phase again. They go back to the same origin again. Okay? So they repeat themselves with a period of 2 pi, which is the fundamental frequency. Yes, there's another question from the back.
Wouldn't they repeat? I mean, isn't this kind of like a lowest common denominator thing? Would they repeat?
Yeah, lowest common divider of all the frequencies. You find the lowest common divider of all the frequencies. And this one does not have the lowest common divider.
Why would 2 just be the lowest common divisor for those ones?
Of this one,
Yeah.
but they're not integer values. Okay, this one will repeat itself with 2 pi over 2. Will repeat itself with a period of pi. But this one will repeat itself with 2 pi over 2 pi with a period of 1. Okay, this repeats itself with a period of pi, this repeats itself with a period of 1. Okay, so they will never be in phase. They will never be in lockstep with each other. No matter how long you wait, you're always out of step with each other.
It doesn't seem like they would never be, right? It would just be a weird number.
Yeah, they will never be
It
locked.
would never be, okay.
Lockstep with each other no matter how long you wait. You start in the beginning, they seem to be lockstep with each other, but you always run out of step with each other. Okay? They will never repeat itself again compared to the beginning of time. Okay? Are there any other questions regarding this? So let's talk about the properties of Fourier transform. Properties are rather simple. If you multiply the function by k, the Fourier transform is just k. Okay, those are some of these are quite mundane. Okay, but this one might be interesting. If ft gives you a Fourier transform of f sub n, all the Fourier coefficients are f sub n, then f sub t minus t naught give you a new Fourier coefficient, which is f of n e to the minus j and omega naught t. Okay, this is something that you might have learned before also for phasors. If you can think of this as a phasor wrap of this, if this is a sinusoidal function. If you were to delay your function by t naught, the phasor wrap will become just this one. Okay, you have seen this property in phasors as well. Okay. And then you have this property, if f of t gives you f sub n, then d dt of f of t will give you j n omega naught f sub n. This is something that you have seen in phasors as well. Okay, you can prove that very easily because the Fourier expansion is nothing but expanding an arbitrary signal in terms of the set of phasors, sums of phasors. Okay, so some of the phasor properties that you have learned before still holds true. Okay, and then you have this, if f of t is real, okay, it implies that f sub minus n is f sub n conjugate. I think we proved this before. Okay, and then you have even an odd function. You have another one which is I think you haven't been taught that before, average power. That if you take the average power of a signal, okay, and find the power over one period, this is you square the signal and find its average, the time average power over one period. This is just the sum of the Fourier coefficient square. We will prove this later on in the course. Okay, I think these are the few properties that you should be aware of. This one is not immediately obvious to you because you never had this before. Okay, but this one you kind of have it before when we proved the compact form, when we proved the trigonometric form and the kind of thing. We did make use of this property. This is a property of phasor. Okay, this is a property of phasors too. Okay, but this is something new, very new, and we'll prove this later on. Are there any questions regarding these properties? Yes?
So the right-hand side is phasor things, right?
The right-hand side are the Fourier coefficients.
Yeah, so if you, for the second one, why is there like a t in the exponent? Why would the coefficient?
Oh, sorry, this is n naught, t naught. Okay, I think I have it wrongly, yeah. N naught, t naught. Okay, like what you saw in phasors. Okay, if you have this, then the Fourier coefficient will just become that. Okay. And then this is true, this is true. This is something very new to you. Okay.
So none of that is this time.
Are there any questions regarding this? We can prove this property very easily. So if I were to replace this with that, then I would just have this. Okay, f of n e to the j n omega naught t minus t naught. Okay, and I can rewrite this summation, lumping that over e to the minus j omega naught t naught e to the j n omega naught t. So this is a new coefficient. This is f n prime. So I will get a new coefficient with this proof very easily. So you can see that if you time delay a signal, its Fourier expansion will just have a new coefficient given by this. Okay? I think the other ones you can prove quite easily too, except for this one. This one is kind of hard to prove. Okay? This one will be hard to prove. We'll prove that next time. Okay?